Hi, we're going to cover octal and hexadecimal. You'll see that I've done some longer videos. Feedback was they were in depth, lots of background knowledge, really informative, but they're a little bit long if you just want quick answers and a quick run through. So my plan is to do quick videos of run throughs and longer videos for background knowledge. So here we go with octal and hexadecimal. Right, let's get going. So we've got octal, hexadecimal, decimal and binary. Right, so octal is to the power of 8, hex is to the power of 16, and decimal is to the power of 10, and binary to the power of 2. What does all this mean? Well, if we'll use decimal because it's the quickest and easiest to explain. You'll get this from school, but decimal 1 times 10, i.e. power of 10, is 10 times 10 is 100. So if I write 111, you know, because you're used to this, that equals 111. Why does it equal 111? Well, we've got 1, 100, 1, 10, and 1, 1. It works exactly the same in hexadecimal, octal and binary. So let's do it in octal. Octal is 1, and as we'd add power of 10 here, we'll do a power of 8. So 1 times 8 is 8, 1, and 8 times 8 is 64. So 111 in octal equals 64, and 8 and 1 equaling 73. Exactly the same with hexadecimal. We've got 1 times 16, which is 16, times 16 is 256. 1, 1, 1 equaling 273. Binary, 1 times 2, as we have here, is 2 times 2 is 4, so 1, 1, 1 equals 7. Hopefully that helps. Why do we use binary? Computers like electric, they like it to be turned on, turned off. That's how we can communicate with them. So we have two states. We have 0 and 1. They're the only two states we have. That's the only way we can talk to them. So we can send them 1s and 0s. So let me choose a number. How do you indicate octal? With a 0. How do you indicate hexadecimal? With a 0 and an X. How did I remember these? O for octal and an X for hexadecimal. It is 0, but hey, it helps. To represent binary, you should and could write this. Right, I digress. So we need to, what we're going to do is we're going to choose two numbers, and we're going to add them together, and we're then going to break them down again into their octal and hexadecimal counterparts, and we're going to represent it in binary. So number I'm going to choose is octal 1, 1, 1 and 1, 1, 1. Easy because we can use these two decimal numbers, add them together. 3 and 3 is 6, 7 and 7 is 14, and 2 with the carried 1 is 346. So let's remember that number quite quickly. Right. So these two should equal, when finished, equal this. But if we add those together. So let's break them down. How do we break them down? Well, octal needs 8 digits. So we want 0 all the way to 7. How to represent 7? In binary, 1, 1, 1. So we know we only need 3 binary digits to represent all the way from 0 to 7. 1, 0, 0 being number 1 of our digits, all the way up to 7. Computer science, everything starts at 0. Your hash maps, array lists, etc., etc., all their indexing is 0, but we'll get to that another day. So we've got 0, 1, 2, 3. Why is this making any sense, do you think? Well, 1, 2, 3. So we go all the way through to 7. Right, so that's going to be 3 digits. Hexadecimal is exactly the same, but it needs to go up to 15 to give us the full 16 sets of digits. So we go 0 all the way to 9, and then we get a little bit stuck because we can't represent 10 in one digit. So you'll be wondering what this is all about. Well, if I want to represent an 8, I'd colour each one of these in as is. But if I turn to the alphabet to go to represent 10, I can colour this one in, this one in, this one in, and this one in, this one in, this one. There's an A. Well, what we do in hexadecimal is we go 0 to 9, then we go A, B, C, D, E, F, giving us the extra 6 that we need, plus the 9, equaling 16 digits, or 0 to 15. Right, this will come in handy in a second. Right, so we're going to now take octal 111 and hexadecimal 111. It's easy. What we do, take the first digit. There you go. Oh no, we didn't. It's not that easy. So that represents that one. That one is represented by that one. And that one is represented by that set of binary digits. And as if by magic, 1, 2, 4, 8, 16, 32, 64, we've got exactly as we had earlier, which is 64, 8 and 1, which is 4, 5, 13 and 7, 73. So we'll do the hexadecimal quickly. But we're going to use 4 digits, because that would equals 15. So 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. I can't put an extra 3 in here. This means nothing. So add them together. 1 add 1 is 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0. If I want to break them back down into octal, there's 3, so and another 3, so that will equal 2, that will equal 3, and our last one equal 4, and 1 is 5, so we now have octal 5, 3, 2. Break it down into hexadecimal, take 4 of them, so that's 2 and 4 is 6, not 8 and 2 is 10. 4, take the next 4 digits, 1 and 4 is 5, I'll take the last 4 is 1, so we've got 2x 1, 5, and the problem is we've got 10. If you remember back, we went from 9 to A, so 10 is represented by A, so we have 0, 5, 3, 2 and 0x 1, 5, A, and if you take all this together, you take 2, 4, 8, take 16, 64, 256, you'll find 8, 10, 16, 20, 26, 1, 7, 12, 14, add the 1 is 346, and as if by magic, 346. There you go. So hopefully that might help. You never know.